Today we are going to go over eigenvalues and eigenvectors. I am going to assume that you already know how you can apply a matrix to a point P to transform it to a new point. I'm going to assume you know how to multiply two matrices together. I'm going to assume you know about invariant lines and also preferably lines of invariant points. And finally, I'm going to assume you know what the inverse of a matrix is and how you can calculate it for 2x2 and 3x3 matrices. So let's first do a little experiment. Consider the matrix M, which is 4, 2, 1, 3. If we wanted to work out its invariant lines, which we can say is y is mx plus c, if we apply the matrix 4, 2, 1, 3 to a point x1, y1, we get 4x1 add 2y1, x1 add 3y1, which is equal to big X, big Y, which will also exist on the line y equals mx plus c. So big X is equal to 4x1 add 2y1, big Y is equal to x1 add 3y1. Due to the invariant line, we know that y1 is equal to m x1 add c. So we can say that big X, is equal to 4x1 add 2 x1 add c, which is 4x1 add 2 x1 add 2c, which is 2m add 4 x1 add 2c. Also, we can say that y is equal to x1 add 3 mx1 add c, which is equal to x1 add 3mx1 add 3c, which is 3m plus 1 x1 plus 3c. So we also know that big X, big Y exists on the same invariant line. So big Y is equal to m big X plus c. So 3m plus 1 x1 add 3c is equal to m 2m plus 4 x1 add 2c plus c. So 3m plus 1 x1 add 3c is equal to m 2m plus 4 x1 add 2mc plus c. 3m plus 1 x1 add 3c is equal to 2m squared add 4m x1 add 2m plus 1c. So if we take everything to the right hand side, 2m squared add 4m take away 3m take away 1 x1 add 2m plus 1 take away 3c is equal to 0. 2m squared add m take away 1 x1 add 2m take away 2 c is equal to 0. x1 cannot be equal to 0, so we need to have both 2m squared add m take away 1 equals 0 and 2m take away 2c equals 0. So we need both of these to be the case. So we can, for 2m squared add m take away 1 to be 0, we get m is equal to 1 by 2, m is equal to minus 1. For 2m take away 2 multiplied by c is equal to 0, we get 2m take away 2 equals 0, so m equals 1, or c equals 0. However, if m is equal to 1, 2m squared add m take away 1 is not equal to 0, so we ignore it. Therefore, m equals 1 by 2 or m equals minus 1, and c equals 0. So we have two invariant lines, y equals 1/2 x, y equals minus x. So let's consider these lines on a graph. Let me draw a set of axes. Let's so this here is y equals 1/2 x, and then this here is y equals minus x. Let's consider a certain point on y equals 1/2 x. 2, 1. When we apply the matrix M 4, 2, 1, 3, 2, 2, 1, we are expecting that it will move to a different place on the same line, y equals 1/2 x. So 4, 2, 1, 3, 2, 1 is equal to 8, add 2, 2 add 3, which is 10, 5, which also will, this is definitely not to scale by the way, also exist on y equals 1/2 x. Let's also consider a point on y equals minus x. Let's say 1 minus 1. 4, 2, 1, 3, 1 minus 1 is equal to 4 minus 2, then 1 minus 3, which is 2 minus 2. So, for a point on y equals 1/2 x, for example 2, 1, 2, 1 was mapped to 10, 5. And for the graph, for the line y equals minus x, 1 minus 1 was mapped to 2 minus 2. So what we notice here is that these coordinates have been multiplied by 5 for the graph, for the line y equals 1/2 x, and for y equals minus x, it was multiplied by 2. The graph y equals 1/2 x, we can represent it using vectors. R is equal to lambda lots of 2, 1. So yeah, so y equals 1/2 x, and y equals minus x, r is equal to mu 1 minus 1. So 2, yeah. So these here represent the two different lines, y equals 1/2 x and y equals minus x. So our eigenvalues are the 5 and the 2, and the corresponding eigenvectors are v1 is equal to 2, 1, v2 is equal to 1 minus 1. So what we are saying is that, lambda, when the matrix M is applied to a point on the line going through the origin, r is equal to lambda lots of 2, 1, well not lambda, let's say, I shouldn't have put lambda, let's say t. If we have the matrix M applied to a point go on the line y is equal to t, y is equal to 1/2 x, or r is equal to t lots of 2, 1, then it gets mapped to a different point on the same line, and the scale factor in which the coordinates have moved is the eigenvalue. And this is how eigenvalues and eigenvectors work. The eigenvector represents the invariant line, and the eigenvalue represents the scale factor in which where the point on the original eigenvector will move after the matrix is applied. So, if we had to simplify this, let's start using some more sophisticated terminology. Let's say the matrix M has eigenvalue lambda, let's say an eigenvalue lambda and a corresponding eigenvector V. When M is applied to a point on V, it gets mapped to a different point on the same eigenvector. So R is equal to lambda V, or I'll put T. So if the matrix M is applied to a point on R is equal to TV, then it gets mapped to a different point on the same line. So MV is equal to lambda V. And we can rewrite this as MV is equal to lambda IV. You might be wondering why we could just do something like this. Well, let's say that V is equal to A, B, C, and lambda V is equal to A lambda, B lambda, C lambda. Lambda IV is equal to lambda multiplied by 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, ABC, which is lambda, A, B, C, which is A lambda, B lambda, C lambda. So we can conclude that MV is equal to lambda IV. So if we take everything to the left, M minus lambda I V is equal to O. M minus lambda, let's say M is A, B, C, D, E, F, G, H, I. M minus lambda I would be A minus lambda, B, C, D, E minus lambda, F, G, H, I. I minus lambda. M minus lambda I V would be A minus lambda, B, C, D, E minus lambda, F, G, H, I minus lambda. And then multiply this by the V, X, Y, Z is equal to O. A minus lambda X plus BY plus CZ is equal to 0. This is because I'm multiplying and then everything would be 0, 0, 0. Dx add E minus lambda Y plus CZ is equal to 0. Gx add Hy add I minus lambda Z is equal to 0. What's important with eigenvectors is that the eigenvector cannot be equal to O. The reason for this is because if the eigenvector was O, then every point would be mapped straight to the origin. But we want to find the vector or the straight line, the invariant line, so it can't just be the origin. So this here, a minus lambda x plus by plus ... is a set of 3 planes. And in order for m minus lambda I v to be O, without v itself being O, we require the determinant of m minus lambda I to be 0. So why is this? This set of 3 planes, if the determinant is equal to 0, they will intersect with an infinite number of solutions. If you've done the geometrical interpretations of planes, you will understand that you can have planes forming a sheaf. You can have 2 of the same plane and then 1 intersecting. So again, an infinite number of solutions. And what else is there? I think that's about all I can remember. But there might be more, you'd probably just need to check. So if the determinant of m minus lambda I is equal to 0, you get a set of 3 planes which intersect with an infinite number of solutions for x, y, z, which will also go through the origin. So this here will be your characteristic equation. Determinant of m minus lambda I is equal to 0, and m minus lambda iv is equal to O is the other part which will be very important when working out the eigenvalue and the eigenvectors. Well, mainly the eigenvectors. So let's go back to our previous example. M is equal to 4, 2, 1, 3. M minus lambda I would be equal to 4 minus lambda, 2, 1, 3 minus lambda. The determinant of m minus lambda I is equal to 0. So the determinant of m minus lambda I is 4 minus lambda, 3 minus lambda, take away 2, which is lambda squared, minus 4 lambda minus 3 lambda, which is minus 7 lambda, add 12, take away 2, which is lambda squared, minus 7 lambda, add 10, equal to 0. So lambda take away 5, lambda take away 2 equals 0. Lambda equals 5, so lambda 1, lambda 2 is equal to 2. What we also know is that m minus lambda I v is equal to O. So let's first consider lambda 1 is equal to 5. 4 minus lambda, so 4 minus 5 is minus 1. 2, 1, 3 take away 5 is minus 2. xy, where v is equal to xy, is equal to O. So you get minus x add 2y, x take away 2y equals O. So x minus x add 2y equals 0, x take away 2y equals 0, both result in 2y is equal to x, y is equal to 1/2 x. So this here represents your invariant line. However, it's important to note that we want it as a vector form. So if we set x is equal to t, then y is equal to 1/2 t. So therefore the eigenvector is equal to t 1/2 t, or all we require is that it's parallel, so v is equal to 1/2 or 2 1. So this here is v1. So it's the corresponding eigenvector for the eigenvalue lambda 1 equals 5. Now let's consider the second eigenvalue, lambda 2 is equal to 2. So m minus lambda I v is equal to O. So 2, 1, 1, xy is equal to O, where v is equal to xy. So 2x add 2y is equal to 0, x add y equals 0, y equals minus x. So let's set x equals t. If x is equal to t, y equals minus t. So v2 is parallel to t minus t. So v2 is equal to 1 minus 1. So our eigenvalues are lambda 1 equals 5, lambda 2 equals, 2, and the corresponding eigenvectors are 2, 1, 1, minus 1. Let's consider doing this in 3D. Let's say we have the matrix M equals 2, 2, 1, 1, 1, 2, 0, 0, 2. M minus lambda I is equal to 2 minus lambda, 2, 1, 1, 1 minus lambda, 2, 0, 0, 2 minus lambda. So the determinant of m minus lambda I equals 0. The determinant of m minus lambda I is equal to, let me make sure I do all this right, 1, 1, 2, 1, yep. Yeah, so the determinant of m minus lambda I is 2 minus lambda, 1 minus lambda, 2 minus lambda, take away 0, so it'd just be like this, minus 2, lots of 2 minus lambda, take away 0, add 1, lots of 0, take away 0, so it'd be 0. So this is equal to 2 minus lambda, 1 minus lambda, 2 minus lambda, minus 4 add 2 lambda, which is equal to lambda squared minus 4 lambda add 4 multiplied by 1 minus lambda, minus 4 add 2 lambda, which is lambda squared minus 4 lambda add 4 minus lambda cubed add 4 lambda squared minus 4 lambda minus 4 add 2 lambda equals 0. So we get minus lambda cubed add 5 lambda squared, so minus lambda cubed 5 lambda squared, minus 4 minus 8 add 2 is minus 6, so minus 6 lambda, and then 4 take away 4 is 0. So the eigenvalues we get are lambda 1 is equal to 3, lambda 2 is equal to 2, lambda 3 is equal to 0. So let's first consider lambda 1 equal minus 3. So m minus lambda I v is equal to O, where v is the eigenvector. So 2 take away minus 3 is 5. Oh no, it's just 3. So 2 take away 3 is minus 1, and then 2, 1, and then 1, minus 2, 2, 0, 0, minus 1. Let me just make sure, minus 1, 2, 1, 1 minus 1, 1 minus 2, 2, and then 0, 0, minus 1. Yeah. X, Y, Z is equal to O. So we get minus X, add 2Y, add Z is equal to 0. X minus 2Y, add 2Z is equal to 0. And we get minus Z is equal to 0. So Z equals 0. So now these two top equations can be rewritten as minus X add 2Y equals 0 and X minus 2Y equals 0. If we set Y equal T, X minus 2T equals 0, so X equals 2T. So the eigenvector for the eigenvalue 3 would be parallel to 2t, t, 0. So the eigenvector will be 2, 1, 0. Let's consider the second eigenvalue. Lambda 2 is 2. So m minus lambda I v is equal to O. So we get 0, 2, 1. Then we get 1, minus 1, 2, and then 0, 0, 0, x, y, z equals O. Let me just make sure. So 2 take away 2 is 0, 2, 1. And then, where is it? Oh, 1 minus 1, 2. And then 0, 0, 0. Yeah. So this results in 2y plus z is equal to 0. X minus y add 2z equals 0. And we get 0x add 0y add 0z is 0. So if we set y equal to t, 2t plus z equals 0, z equals minus 2t. So x take away t, add 2t equals 0, x equals t take away 2t, which is minus t. So 2y plus z is 0, so 2t plus z, so z is minus 2t. X take away t plus 2t is equal to 0, x is t minus 2t, which is minus t. So v2 will be parallel to minus t, t minus 2t. So the eigenvector corresponding to 2 would be minus 1, 1, minus 2. Finally, let's consider the final eigenvector, lambda 3 equals 0. I've just realized I've made a mistake on this section. So x is equal to y minus 2z, which is equal to t minus 2 multiplied by minus 2t, which is t add 4t, which is 5t. So v2 is parallel to 5t, t minus 2t. So v2, the eigenvector corresponding to the eigenvalue 2, is 5, 1, minus 2. Now let's go over lambda 3 is equal to 0. So m minus lambda I v is equal to O. So 2, 2, 1. Then 1, 1, 2. and then 0, 0, 2, x, y, z is equal to O. So 2x add 2y add z equals 0, x add y add 2z equals 0, 2z equals 0, so z equals 0. Therefore, these two can be rewritten as 2x add 2y equals 0 and x add y equals 0. Let y equal t, x is equal to minus y, which is minus t. So the final eigenvector will be parallel to minus t, t, and 0. So it would be parallel to minus 1, 1, 0. Therefore, our three eigenvalues are lambda 1 is equal to 3, lambda 2 equals 2, lambda 3 is equal to 0, and the corresponding eigenvectors are 2, 1, 0, 5, 1, minus 2, minus 1, 1, 0. So this is how you would work out the eigenvalues and eigenvectors for a 3D matrix. Thank you for watching.